So good evening, everyone. We'll start our live session on week 6 content. This is the NPTEL course Fabrication Techniques for MEMS-based Sensors Clinical Perspective. The course instructor is Professor Hardik Jitendra Pandya from Department of uh, Electronic Systems and Engineering, ISC. And I am the course TA, Rayan Jasma. I'm from ISC. So first, every week on Monday from 6 p.m. to 8 p.m. I have the live session where I discuss some problems regarding the content that is covered in the week. So this is my meeting link, and if you have any doubts, you can reach me at rayanrjesma@gmail.com. Okay. So first, let us move on to the first problem. Okay, so in problem 1, this is related to lithography. The photoresist layer is exposed to A. Visible light, B. Ultraviolet light, C. Infrared light, and D. LED. So which light do you think is the photoresist uh, layer is exposed to? Okay. So like each of these light has a particular wavelength, right? So the answer is ultraviolet light. And so if you see the photoresist, it is a highly sensitive and it is a chemical substance that is generally used to form any patterns. And this photoresist is sensitive to a particular band of light. And this when we expose this photoresist to that particular band of light, then there will be some change in the photoresist. So, like depending on whether we have a negative resist or positive resist. So, if we have the changes will be different. So, if we have a positive resist and if we expose it to a specific wavelength of light to which it is sensitive to, then the exposed region dissolves in the developer. Mm. But in the case of negative resist, the exposed region hardens, or you can say it cross links. Yeah. So, and the wavelength of light that is generally used for exposure is the ultraviolet light. So, like if you see the wavelength, like in visible light, the wavelength is very large. So, like we cannot fabricate features which are very small resolution. So, as the wavelength of light increases, the resolution also, like the minimum feature that you can fabricate also increases. The size of the minimum feature that you can fabricate also increases. So, in the case of like resolution, we also refer it as critical dimension CD. So, this can be either the minimum, the dimension uh, of the smallest feature, or it can be the gap between two smaller, like the smallest gap between two features. Okay, so CD is called as critical dimension. So it is a measure of the resolution. So if we compare the other options here, the wavelength is larger. So the resolution is also higher. And in like lithography, we can fabricate up to nanometer resolution features. So if you see ultraviolet light, there are like various wavelengths of light which are used mainly for exposure. So in standard photolithography, we have 436 nanometer, which is G line, 405 nanometer, which is H line, 365 nanometer, which is I line. And so in order to fabricate even smaller structures, the wavelength will start will move towards smaller wavelength. So these are all the bands or the spectral lines of a HG lamp. Spectral lines of a mercury lamp. So in most of the tools, we would see either 365 nanometer or 436 nanometer wavelength that is used to expose the photoresist layer. So generally, photoresist layer is exposed using ultraviolet light, and the component of the photoresist which is sensitive to this light is a photoactive component, photoactive compound. So this photoactive compound will change its properties depending on the wavelength or intensity of the light to which it is exposed to. Okay. So is this clear? Okay. So now let's move on to the next question. Problem number 2. Base resistance value of chrome gold IDE structure. So IDE is interdigitated electrode. With a spacing of 50 microns, and 15 microns is X ohm and Y ohm respectively. What is the relationship between X and Y? So option A is X is less than Y, B, X is greater than Y, C, X is equal to Y, which is high Z. So Z is impedance, both are 0. So what do you think the correct answer is? Okay. Let us see how does an IDE structure look like. So we have like two comb-shaped electrodes which are arranged in some interleaving fashion, like this. Hmm. So what is mentioned is that first we have a chrome gold IDE structure which is having a spacing of 50 microns. So the spacing between these two is 50 microns. So like for this kind of structure, the resistance is given as XO. And for the second structure, where we have a spacing of oh, so where we have a spacing of 15 micron between the two interdigitated electrodes. Sorry, spacing of 15 micron between two interdigitated electrodes. So this is 15 micron in the second case. And if you look at the resistance for this structure, it is given as Y1. So now what you have to find is you have to find the relation between X and Y. So like do you think whether the resistance is high or is it low, or like which of the options does this satisfy? So that is what is asked in this question. So what do you think the answer is? Okay. So if you look at an IDE structure, what we'll have is we'll have uh, like if we see the fabricated structure, we'll have a silicon wafer. Then on top we'll have SiO2. Then we'll have the patterned metal electrodes, so which is made of chrome gold in our case, right? Between these two IDEs, there is nothing. So like it is air. There is like no path for conduction. So the resistance will be generally high. And since in this case, we are not just looking at the real part. So we also have to look at the imaginary part of the impedance, like imaginary part, so which will include the reactance. Uh, so the reactance has components like inductance and capacitance. So for IDE structures, what we will be measuring is the impedance, which is the combination of the real part, which is the resistance, and the imaginary part, which is the reactance. So since between IDEs we do not have a conductive path, then generally we know that the impedance will be very high. So the answer is option C. Okay. Like how do we use these kind of structures in like for our applications? Like we'll place some kind of analyte or something in between the electrodes, and depending on the conductivity of the sample, the impedance of the effective structure will change. So here the impedance depends on the conductive path between the two IDEs and not on the gap. So irrespective of whether the size is 50 micrometer, the gap is 50 micrometer or the gap is 15 micrometer, still the medium between the two is air, which is not like it's not a conductor, right? So the impedance will be very high. Okay. So the answer is option C. X equal to Y, high Z. So high Z means high impedance. And this will be maybe in mega ohms, several mega ohms. If we have some sort of fluid between them, then the impedance will be very less. Okay. So is this clear? So this is clear. Then we can move on to the next question. Okay. So now, now let's move on to the next problem. Okay. Problem 3. For the measurement of electrical properties of a tissue, a device is fabricated. What are the process steps to be followed? Okay. So, as we saw in the previous problem, we use a IDE structure, which is interdigitated electrode, in order to fabricate the particular device. So, and we know that for a cancer tissue, we can measure like some properties by using MEMS based sensors. So some of these properties are mechanical, electrical, and thermal. So in mechanical, we'll measure the stiffness. In electrical, we measure the conductivity. In thermal, we measure the thermal conductivity. So in electrical, we can also measure the conductivity or impedance. Okay. So like how does the structure that we are using to measure the electrical properties look like? It's an IDE. So from the top side, we can see we'll have some interdigitated electrodes like this. So here, what you have to do is you just have to tell the sequence of steps which are used to fabricate this kind of structure. So first we have wafer cleaning, oxide deposition, metal deposition to fabricate IDE, metal deposition to fabricate the heater. So what do you think is the sequence that is used? Okay. So what do you think is the sequence of steps that are used in order to follow this process? So fabrication is like there are certain sequence of steps which we will follow in order to get a device. So first we always start with cleaning the wafer because we want to remove all the contaminants that are present in the wafer. And I think in the last week discussion session, we saw that there were different types of contaminants like organic contaminants, inorganic contaminants, and as well as metallic or ionic contaminants. And in order to remove each of them, we have some different cleaning processes as well. Like most of them are acid based. So first, and like some are solvent based. So first, if we look, the first process will be to start with wafer cleaning. So this will be process one, first one. Okay. Then next we have to, we will be normally starting with a silicon wafer. So which we have a silicon wafer here. And then we know that like when we deposit a metal directly on silicon, like there can be some conductive path through the silicon. So to avoid that, we will start with oxide deposition. Okay. So next we will go with the oxide deposition, SiO2. So this will be the second step. Then in the third step, what we will do is we will have to fabricate the heater. So we'll pattern the heater by using lithography, and then we will do deposition. We can use either evaporation or sputtering. So this will be our heater. Then we have to fabricate the IDE. So we are using heater in this case because like by measuring the electrical properties at a higher temperature, we can get better sensitivity. And since both the IDE is an electrode which is made of metal and the heater is also made of metal, we don't want the two structures to short with each other. So we'll have to deposit some sort of insulating layer between them. And this insulating layer is SiO2. So again, we will go with the deposition of SiO2. That will be the fourth step. And then in the final step, we will do metal deposition to fabricate the IDE. So that is a final step. So if we look at the stack, what we will have is we will have ID at the top. Then we'll have SiO2. Then again we will have the heater electrodes. Then again we'll have SiO2. And then we'll have silicon. Okay. So since we don't want a conductive path between the metal and the silicon, we have a SiO2 layer in between them. And also we don't want the interdigitated electrode to short with the heater. So we'll have another SiO2 layer between them. So the answer for this is first is wafer cleaning, second is oxide deposition, third is metal deposition to fabricate the heater, Fourth is again oxide deposition. And in fifth, we'll do metal deposition to fabricate the interdigitated electrodes. So is this clear? So now let's move on to problem 4. Properties measured using ETM sensor for breast cancer tissue phenotypic are. So ETM is electrical, thermal, and mechanical. Okay. So this is a MEMS sensor which is used to characterize the breast cancer tissue and in order to determine whether a person is having breast cancer or not. So the options are option A, capacitance, elasticity, specific heat. Option B, capacitance, viscosity, thermal conductivity. Option C, resistivity or resistance, elasticity, thermal conductivity. Option D, resistivity or resistance, viscosity and specific heat. So like you just have to find which property we are measuring for electrical, thermal and mechanical in that order. Like which properties we generally measure, not in this order, in any order, but what properties like we generally measure in order to characterize the tissue. So what do you think the answer is? Okay. So the answer is option C, resistivity, elasticity and thermal conductivity, right? So thermal conductivity is a property that we are using to measure for thermal. Elasticity is for mechanical, and we measure the resistivity or resistance, or in some cases, generally we can say it as impedance for the electrical property. Okay, we are not measuring the specific heat of the structure, so option A is wrong. Then we are not measuring viscosity, so it is a tissue, right? So we are not measuring the viscosity of the tissue, so this is also wrong. And since option D is having both specific heat and viscosity, this is also wrong. So the correct answer is option C, which is resistivity or resistance, elasticity and thermal conductivity. Is this clear? So if this is clear, we can move on to the next problem. So this is related to SU8, which is related to the lithography question. SU8 is a negative photoresist. Areas of wafer covered with SU8 when exposed to UV light will option A harden, B soften, C remains the same, D cannot be determined. So we know that like photoresist has various components, and like these components, when they are sensitive to particular wavelength of light, when they are exposed to the wavelength of light to which they are sensitive to, then the properties will change. So in this case, what changes is their solubility to the developer will change depending on the intensity of light as well as the regions which are exposed or the regions which are not exposed. And we also know that there are two types of photoresist, negative and positive photoresist, which will exhibit different behavior when it is exposed to UV light. Okay, so which one is the correct answer in this case? And here it is mentioned that SU8 is a negative photoresist. Okay. So the correct answer is option A, harden. Okay. So what happens is in the case of a positive photoresist, let's say we are having a pattern like this. This region is chrome. We are having a mask. and this region is transparent, this region is opaque, and we are having our sample which is coated with photoresist. And this is positive photoresist. Okay. So what happens is the light will pass in these regions, the transparent regions, which is generally the mask is made of soda lime, or in certain cases a more expensive mask will be made of quartz. So the regions which are getting exposed to the light will have more solubility in the case of positive photoresist. So these regions will be more soluble and they will easily get dissolved. So if you see here, these regions will easily get dissolved. And if you see the negative, what happens is after we dip the sample in a developer followed by DI water wash, then we will see photoresist only in this region. So in the region where there was no light exposure. So only in those regions we will see the photoresist remaining. But in the case of negative resist, so what happens here is the exposed regions have a better solubility for the developer. In the case of positive photoresist, in the case of negative photoresist, what happens is that like if you consider the same case where we are having a mask and if we are using the same mask, so here the exposed regions will harden. So they the photoresist undergoes something called cross-linking, and this region, which is unexposed region, will become more soluble. Okay. So here, this is the soluble part. So this is negative photoresist. So here what happens is wherever the light is exposed, the photoresist undergoes something called cross-linking, and this will cause the photoresist regions to harden, and the region which is not exposed will be softened. So here what is asked is the areas of the wafer covered when exposed to UV light will harden. So the answer is option A, harden. Okay. So the answer for problem 5 is option A, harden. Now next we'll move on to next. A typical photolithography processes involves the following process, put in correct sequence. So we have some steps. One is spin coat photoresist, mask loading and exposure, stripping photoresist, etching, soft bake, hard bake, and developing. So what is the sequence of steps that we follow in order to do a photolithography process? And here you can consider like we are using a positive photoresist. Or yes, can consider that you are using a positive photoresist. So what do you think are the sequence of steps? So generally, uh, uh, generally we'll start with cleaning the wafer, which is not listed here, but still, first is we will clean the wafer. Okay. Then we will dehydrate it. So this is to remove any moisture that is present. If there is moisture on the substrate, what will happen is the photoresist will not get adhered to the substrate. It will not stick to the substrate. So we have to remove any moisture that will be present during the cleaning process. And for the cleaning process, generally we will do solvent cleaning, which will consist of dipping the sample in acetone, then IPA. This is then followed by DI water rinse. So once we wash with lots of DI water, then we'll have to dehydrate the sample so that we can remove all the water content that is present in the sample. Then next we will do is spin the photoresist, spin coat the photoresist. So in spin coating process, what we will do is we'll place the sample on a vacuum chuck. Then we will dispense the photoresist on it. So the photoresist is a liquid. It will have photoactive components, some polymer and some solvent. So it is generally in liquid phase. We'll pour this on the sample. Then we will set some parameters like the rotation speed and the rotation duration, which are which will determine how much thickness of the photoresist we have in addition to the viscosity of the photoresist. Let's say like certain and if you look at various photoresist, some of them are AZ4562, AZ5214, S1813. So here in these photoresist, the last two digits will tell you how much thick the photoresist is. So if it is 62, then the photoresist will be around 6.2 micrometer thick. But if we follow the standard parameters, so for this one it will be around 1.4 micrometer if we follow the standard parameters. But again, the thickness can be varied by varying the rotation as well as the duration of the spin. We can so in the data sheet of the photoresist, they will have some range of values, uh, range of thicknesses of the photoresist, which we can obtain by using a particular speed or particular duration. So that the third step is spin coating the photoresist. Then next what we'll have to do is before doing exposure, we have to remove some of the solvent. We have to make the photoresist somewhat thick. So we will follow this by soft bake. So soft bake is when we will do baking at for a very short duration, and this is done generally to remove some of the solvent, not all the solvent, not to harden the photoresist, but to remove some of the solvent so that it becomes somewhat thicker and it will become more photoactive to the wavelength. So next we will follow this by exposure. So mask loading and exposure is the next step. Once exposure is done, like during exposure, what happens is like the light will pass through certain regions of the mask. The regions of the mask which are transparent will allow light, and the regions which are opaque will not allow light. And depending on the type of resist that we use, so if it is a positive photoresist, the regions which see the exposure of light will become soluble in a developer. So their like solubility changes. So next step will be to develop. So in which we will put the sample in some developer, and generally these developers are base, like they are some kind of base. In order to stop the development, we put the sample in DI water. So DI water will stop the developing process, and this development is generally done for certain amount of time. So a specific amount of time depending on the exposure dose, your parameters, and also depending on your feature sizes as well. Then after developing, we'll have to do hard baking. So hard baking, in hard baking step, what we will do is we'll bake, but we'll do it for a longer time so that we will remove all the solvent that is present. Okay. So we'll remove all the solvent that is present, and the photoresist will become very hard. So then we will follow this by the etching process. So here the process that is mentioned is etching. So next we will follow it by etching process. Okay. So is this clear? So if we look at the answers, first is to spin coat. This is the first one. Then we will follow by soft bake, then mask loading and exposure. Uh, then at the last step, we will strip the photoresist once the etching is done. Okay. Mask loading and exposure. Then we will follow it by developing. So in developing process, we will have like what will happen is we will have that some regions of photoresist will remain, some regions will get dissolved. So in the regions where the photoresist dissolves, we will see the substrate, whatever substrate is there. Then after developing, we will do hard bake in order to remove all the solvent that is present, and the photoresist will become like a thick, a film, a hard film kind of film. Then we'll go with the etching process. So in etching, we will remove some portion of the substrate, and what happens is if we have photoresist here in the regions like this, then the regions where the photoresist is present will be protected, and the regions where you see the substrate will get etched. Yes. So here the photoresist will act as some kind of mask which will protect the underlying regions. Then once your etching process is done, in order to proceed for the next further processing, or let's say it is your end of your process, you don't want the photoresist to remain on your sample, so you will follow this by stripping the photoresist. So the correct answer is this. So these are the correct sequence. First is spin coating photoresist, soft baking, mask loading and exposure, developing, hard baking, etching, and then stripping photoresist. Now let us move on to next problem, problem 7. So this is based on AC-weight. So you would have seen AC-weight used for the piezo cantilever structures. So in this question, we have SU8 material being used in device fabrication in the ETM device. So ETM is electrical, thermal, mechanical device, as well as a piezoresistive micro cantilever device. Which of the following statements are true in this regard? So this is a multiple answer, like a question where multiple answers can be correct. So in option A, SU8 pillars were used in the ETM device to ensure electrical contact to the IDEs. Option B, SU8 was used in the piezoresistive device to transfer force on the piezoresistive material. Okay. So which one is the correct answer? You would have seen, I think, the ETM device, and you would have seen these things, right? Okay. So the correct answer is option B. You know that in the case of no, the correct answer is both option A and B. So in option, if you look at option B, you know that like in the cantilever structure, we had some SO8 pillars which were used to transfer the force like from the tissue. So we'll keep the tissue here. We will like whatever, and we'll use some indenter to poke the tissue, like, and whatever force or whatever stiffness, depending on the stiffness of the tissue, there'll be some force that is transferred to the cantilever through the SU8 pillar. Then in the cantilever, so the correct answer is both option A and B. First, let us look at option B. Why is option B correct? Okay. So you would have seen in the class lectures that uh, in the case of a piezoresistive cantilever, what we will have is we will have a cantilever with a SU8 pillar tip, and then you will have a tissue. So on this tissue, there'll be some, we'll do some indentation using some structure, and then depending on the stiffness of the tissue, there'll be some amount of force which will be transferred to the cantilever, and this force is transferred by using the SU8 pillar. Due to the force that is being transferred to the cantilever, the cantilever will bend, and here we will have some piezo resistor. Depending on, so when the cantilever is bending, there will be some amount of strain which is generated at this portion where it is anchored, stress that is generated at the portion where it is anchored. So depending on how much stress is generated, that will be converted into change in resistance. So option B is correct. Then in the case of option E, you would have also seen that in the case of SU8 pillars, like there was a process where we had to do gold coating over the SU8 plus to make them conductive. So SU8 plus are also used in order to ensure electrical contact with the IDEs. So this is also correct. Okay. So for problem 7, both the statements are correct. Option A and option B are correct. Is this clear? Okay. So now let us move on to the next question. Problem 8. So we have a type of wafer called silicon on insulator wafer, which is SOI for short. It is a special type of silicon wafer. Evaluate whether the statement below about SOI wafer is true or false. So SOI has a thin layer of silicon over a thick layer of silicon, which is separated by thin layer of insulator such as oxide. So what they are mentioning here is that we are having a wafer which is having a thin layer of silicon. So this is silicon. Then here we are having silicon dioxide. Then we are having a thick wafer of silicon. So is this correct? Right. Hi. So I've started the session. I hope like the session will be somewhat interactive. Okay. Am I audible? Am I audible? You can unmute and tell, or you can put a message in the chat. So I'll repeat the question again. Okay. So problem 8 is that silicon on insulator soy is a special type of silicon wafer. Evaluate whether the statement below about the soy wafer is true or false. Soy is having a thin layer of silicon over a thick layer of silicon, which is separated by a thin layer of insulator such as oxide. So like what it is meaning is that we are having a silicon layer, then we are having a silicon dioxide layer, and we are having a silicon layer. The difference between these two layers is that the layer at the top is thin, and the layer this is thin and this is very much thick. So is this true or false? Like, is this kind of wafer called as silicon on insulator wafer? What do you think is the answer? Am I audible? You can tell what the answer is. You can guess. It's fine if you're wrong. It's not an issue. So the answer is true. Okay. So these kind of wafers are like specialized wafers, which play a very important role in fabricating MEMS devices where we have released structures. So MEMS devices means like cantilevers and stuff. So like we'll have, if you fabricate a cantilever, it will look like this, and then handle layer can be like this. Okay. So we have released structures, and like it will help easy fabrication for MEMS structures. And if you see how this kind of wafer is fabricated, there are two methods. One is called as SIMOX. So SIMOX, which means separation by implantation of oxygen. Okay. So here what happens is that we'll do an oxygen ion implant on a silicon wafer, and then like at a particular depth. So there'll be some oxygen rich layer which is formed at the somewhat in the center, and then we'll go with high temperature annealing. So at the high temperature annealing, this oxygen rich layer will like combine with silicon to form silicon dioxide layer. So this is one process by which we can fabricate a soy wafer. So depending on like what energy we give for the ion implantation process, we can like kind of like determine how much depth we want this oxygen layer to be. Okay, there is also another process for fabrication of soy wafer. In this wafer, we will do bonding. So what happens is we'll take a silicon wafer, this is a silicon wafer. Then we'll do surface oxidation, means oxidation at the surface. So this can be thermal oxidation or like which is dry or wet oxidation. Then we'll do hydrogen ion implant. So in hydrogen ion implant, again, what we'll do is we will just implant the hydrogen ions with a high energy, and like they will form some sort of layer at a particular depth below the surface. Then we will flip this wafer. So what we'll do is we are flipping this wafer like this. So the thermal oxide layer will come in the bottom. Then we'll have this small region where we are having some hydrogen ion implant. Then we will bond it with another silicon wafer. So this is our second wafer. This is also silicon wafer. Okay. So second wafer. Then we will what we'll do is due to the ion implantation, there'll be some sort of bubble formation or defects formation at the like region where this hydrogen ion implant has happened. Okay. So in those regions, what will happen is like the silicon wafer will start to break because of like lot of defects along this particular line where the hydrogen ion implant has been done. Then so once it breaks, we will have a very rough surface on the top. So what we will do is we will follow it by CMP. CMP is chemical mechanical polishing. So this we are doing in order to smoothen the surface. So then what will be left is with the silicon wafer, which is having this stack silicon. This is SiO2 and then silicon dioxide. Sorry, and then silicon handle layer. So here in this from this process, you can see that the layer at the bottom is having very much like higher thickness compared to the layer, the silicon layer at the top, right? And also here also, even when we are doing ion implantation, like there is a particular depth up to which we can if you want to go greater depths, then we'll have to give more energy. So there is a limit on how much like depth we can do ion implantation. So one side will be thin and the other side will be thick. So in this case, it will be around 500 micrometer, like for a 4-inch wafer, 500, 550 micrometer for a 4-inch wafer. So this is soy wafer and it's generally used for MEMS fabrication. And so there will be many like there are various wafers depending on different thicknesses. And if you this top layer is also called as device layer. Okay. And this uh, bottom silicon layer is also called as handle layer. The SiO2 layer is also called as BOX. BOX, which stands for buried oxide layer. And the device layer is the layer in which we will fabricate our devices, let it be MEMS devices or even transistors as well. The handle layer is just for like support for the layer. And there are soy wafers with different thickness like 1 micron, 2 micron, 4 micron and so on. All these will come with a box of maybe 1 to 2 micron or like maybe 3 micron in some cases, and a silicon handle layer of around 500 micron or greater. Is this clear? Then we can move on to the next question. In IDE fabrication process or any other fabrication process, acetone dip is used to remove. What's the correct answer? In IDE fabrication process or any other fabrication process, acetone dip is used to remove. Option A is gold, B is nichrome, C is chromium, and D is photoresist. So I think this we saw in one of the previous questions, right? Acetone is a sol. Oh, okay. So the answer is option B, photoresist. So here option A, B, and C, all three are metals, right? Metals. In order to etch metals, we generally use some sort of acid-based etchants in order to remove the metals. Okay. So photoresist is a this is a photosensitive compound which can be easily dissolved in solvent. It also has some amount of solvent and it is readily soluble in solvent as well. So in the first step, we'll do while processing a wafer. Um, like we will do this acetone dip in order to remove any impurities or like any organic contamination, and in this case we can also use it to remove any photoresist. The metals will generally not be affected by this process. Okay, so if you want to remove any metal, you will have to do some acid based etching. You have to use some acid based etchings. So now let us move on to next problem. Problem 10. Evaluate whether the statement below is true or false. For SU8, photoresist development is followed by hard bake. So, one hint regarding this problem is that SU8 is a negative photoresist. And whatever region which is getting exposed will be cross-linked. So, which means that that region is will not get dissolved easily in the solvent, right? Hmm. So, whether is this statement true or false? So the correct answer is false. Okay. Why is that? The like so here you can see um, hmm, hmm. So here you can see various steps that are used in order to for a negative photoresist. So first we will do substrate pretreatment, which means it is a cleaning step. Okay. Hmm. So in the first step we are doing a substrate pretreatment, which is cleaning followed by uh, hmm, plus dehydration. We can also coat a primer if like uh, so we can coat a primer. So this primer will help you in better adhesion of the photoresist. In the coating phase, after coating the primer, we'll spin coat the photoresist. So if your sample is small, then what will happen is at the edge. So the coating of the photo, what happens is we'll dispense the photoresist like this in the center of the sample. Then like the sample is made to spin at a particular RPM. So what, due to the centrifugal force, the photoresist will start to spread. So what happens is like there will be more amount of photo at the edges. You will see that the photoresist layer is somewhat thick compared to the center. So these are called as edge beads. So edge bead removal is the next step. This is mainly for small samples, and generally when you are doing fabrication, we will not keep our devices in the like we will have some boundary region. Like so, if your sample is like this, you will not keep your devices near the edge. You will keep it somewhat in the interior region, and the reason is that like in the region where we have HBs, the photoresist thickness will be very high. So whatever exposure dose or development time that you use for your samples which are in the inside will not work for the outside. So if you do development for long time, in order to develop your devices at the edges, what will happen is your devices in the center will become overdeveloped. So overdeveloped means, let's say you want a box which is 10 micron floss, 10 micron. After development, if you are getting 20 cross 20, so means your dimensions have become larger than required. So this is in the case of a um, positive photoresist. So only in this region you are exposing. Then this is called as overdevelopment. So generally we don't want overdevelopment because we will have some particular design which needs a particular dimension. So then so generally in the edges we will do edge bead removal. This we'll do by pouring some solvent at the like so there will be some sort of setup in the spin coater itself in order to remove the edge beads. Then we'll do soft bake in order to remove some of the solvent. Then we will follow this by exposure. So after exposure, we'll do a post-exposure bake for some time. Then we will follow this by uh, development of the sample, and then we will rinse and dry. So in when we are doing development, what will happen is that the regions which are exposed to light will remain, while the regions which are not exposed to light will get dissolved. And then at the end, we will either do hard baking if we want to do go for etching. Otherwise, we will just like if you want to do metal deposition, then we'll just go like that. So these are the steps. In the case of so this is in the case of negative photoresist. In the case of positive photoresist, what will happen is so this is negative, right? So in case of positive photoresist, we'll have substrate pretreatment, then coating, then we'll have edge bead removal, we'll have soft baking, we'll have exposure. Then we will not have this post-exposure bake. We'll move on to development. Then once it is developed, we'll do rinse and dry, and then we will do hard bake or removal is optional. So like between the positive and the negative photoresist, this step will like kind of change the property of the photoresist. So we'll move on to next problem. SU8 is a option A polymer, B insulator, C negative photoresist, D all of the above. So we already in previous problems we already saw SU8 earlier itself. So what do you think is the correct answer? So we have options. Option A is polymer, option B is insulator, C is negative photoresist, and D is all of the above. So we know that SU8 is a negative photoresist, right? And so photoresist generally consists of polymer, some photoactive compounds, as well as it also consists of some um, solvent. As so it is a polymer, so that is also correct. And you know that SU8 is an insulator. Uh, Most of the polymers are insulators, but there are some conductive polymers as well. And in so where we want, there was one process where we had to do some gold coating over SU8 in order to make it conductive. Right. We were doing that because it was an insulator. So the correct answer is option D, all of the above. So we'll move on to the next question. Problem 12. What kind of mask would you use if what kind of mask would you use while using photolithography to form SU8 pillars? So we like have these SU8 pillars in the piezo cantilever, right? So if you are looking at the pillars, it will look like this. We have pillars like this. So this is SU8. Then we are like, let's say these pillars are on some substrate. If you look at the top view, these pillars are round, so they will look like this. This is cross section or side view. Let's say it is side view. Side view. Oh, this is top view. Mm. And you know that SU8 is what? It's a negative photoresist, right? So in order to make these kind of pillars, what kind of mask would you use? Is it bright field mask or dark field mask? Okay, so uh, like first let me tell what are the different kinds of masks. So depending on like whether we have some opaque region, like some opaque patterns in large region of transparent uh, mask, or whether we have some small transparent regions in in the midst of a large opaque region, we can classify the mask into bright field mask or dark field mask. So in bright field mask we'll have small amount of opaque region and large amount of transparent region. In dark field we'll have large amount of opaque regions and small amount of transparent region. So if you take like cross section along this is the pattern that you will see at this portion. Okay. So what happens is in bright field mask, light will like it will fall through this. It will go through the transparent region. In the dark field mask also, it will go through the transparent region. So the region of exposure is this and this for the bright field, and for dark field it is this. Okay. Next we know that we have two different types of photoresist. One is negative photoresist and the other is positive photoresist. In negative photoresist, exposed region hardens. Here in positive photoresist, exposed region softens. So it gets easily dissolved in the developer. Okay. So here we have some opaque region and here we have some transparent region. So in the case of negative photoresist, after developing, we'll have this kind of pattern. In the case of positive resist, we'll have this kind of pattern. We know that SU8 is a negative photoresist. So we will look at only this side. So if we have a dark field mask like this, then we'll have a pattern like this, right? So where we have some particular like structure along this. And again, interchangeably we can use other, but like what kind of pattern you make on your mask is also important. Okay. So for SU8, like in the case of SU8 pillars, if you look at the top cross section, it looks like this, right? We need some regions like this. Sorry, I'll draw this again. Okay. So what we need is we need some pillars on top of a substrate. So this is SU8 and this is substrate. So from the top view, this is what we will see. So here we can see that by using a dark field mask, we can get that kind of pattern, right? So the correct answer is option B, it is dark field mask. So, and also like it depends on what kind of pattern you are using. Let's say you are using a dark field mask, then how will your mask look like? Okay, this is my mask. In my dark field, I will have large regions which are opaque and small regions which are transparent. So let's say I want to I want to fabricate 3 pillars, then I will have a pattern like this. So where these will be transparent and the remaining regions will be opaque. So what pattern, not only what kind of mask you are using, what kind of pattern you have drawn on the mask also plays an important role, because that will determine what kind of structures we get after fab, in addition to what kind of photoresist you are using. Okay. So the correct answer is option B for problem 12. Next, we'll move on to problem 13. While coating SU8 pillar with chrome gold by the thermal or E-beam evaporation, the sample has to be tilted. Is it true or false? So we know that, and why are we doing this process where we are coating SU8 pillar with chrome gold? That is because we want to make the SU8 pillars conductive, right? And that's why we want to do. And you know that SU8 has high thickness, so these pillars are high aspect ratio structures, which means that like this dimension is very much large compared to this dimension. The diameter of the pillar is small compared to the height of the pillar, right? So if we are doing when we want to do metal deposition, like how we want the deposited metal to be is like this, right? So it should cover the entire pillar, and that the thermal or e-beam evaporation method will is line of sight deposition process. So evaporation is generally line of sight. And what we'll do in evaporation is we'll have let's say we'll have some crucible with the metal that we want to deposit. We'll have our holder and the substrate which will be clamped to this holder. Okay. Then we will melt this material by, so this everything will happen in a vacuum based system. We'll melt this material either by using e-beam or by like thermally by heating the crucible, and whatever vapors, so this is a physical vapor deposition process. Whatever vapors that come from the molten metal will just directly go in a straight path and it will get deposited on the substrate. So what happens is that if you have a profile which is not flat like this, the deposition will happen only in this region and in this region. It will not happen in the side walls. So it is line of sight. So we can say that the whatever evaporated particles will travel in a straight line, not in an angle. So at the end, we'll have some deposition in this and some deposition in this region. We will not have any deposition in the side walls. But in our requirement, when we want to coat a SU8 pillar, we want it to coat the side walls as well, right? And the reason why we want to do that is because like if we just coat this, then there will not be any connectivity between the electrode at the top and the bottom. So like there is a way by which we can resolve, like we can have some coating in the sidewalls as well. And for that what we'll do is we'll keep the sample at some angle. So instead of keeping the sample flat like this, we will keep the sample at an angle like this. So like when if the pillars are like this at an angle, when the vapors come, they will get deposited in the like side of the pillars as well. And also another thing that we do is we'll rotate the substrate in planetary motion, so that we'll have some uniform deposition. So at each point the substrate will be continuously rotating, so we'll have somewhat uniform deposition in the sidewalls as well. So the correct answer is true for problem 13. So the sample has to be either tilted, and in addition to the tilting, we can also have some planetary motion, which will ensure that the sidewalls of the pillars are also getting deposited with the chrome gold. Next, we'll move on to problem 14. Why is chrome used along with gold to form electrode? Option A, to reduce resistance. Option B, for better adhesion. Option C, for heat resistance. Option D, for aesthetic purposes. So what do you think is the correct answer? So in the previous also you saw that we were trying to do some evaporation where we are having chrome and gold. So in this, like the first layer will tell, the first is the layer that is deposited first. So let's say we are having some silicon and so, SiO2 substrate, okay, and we are depositing chrome gold. What we'll do is we'll first do deposition of chrome, then we will follow it by deposition of gold. So why are we using chrome along with gold to form an electrode? Chrome is also a metal, right? We can just deposit chrome, we can deposit only chrome, right? Why do we need something additional like gold? What do you think is the answer? So the answer is for better adhesion. Okay. Uh, Gold has like good resistivity, right? So it is used as an electrode and it is resistant to oxidation. So chrome easily forms oxide. So we don't use just chrome as a layer. Like we don't use just chrome for making an electrode. So we'll have to use a combination of gold and chrome. And when we are doing some electrode, we need it to have like very low resistivity. Like it should be like short. If it is having resistance, then it will affect the whatever we measure, the effective resistance will be from the electrode plus the sample. If the electrode is having higher resistance, then let's say your sample is having like a resistance which is very like less, then you will not be able to detect it, right? So and chrome easily forms oxide, so we cannot use it as electrode. Means it will not have very good resistivity. It will have very like poor resistivity when it forms an oxide. And gold is not having very good adhesion with the layers like substrates like silicon SiO2. So what we'll do is we'll use some sort of adhesion layer like chrome, and we'll use very thin layer. So let's say you want 200 nanometer of gold electrode, you'll deposit maybe 10 nanometer or 20 nanometer of chrome. This will be followed by 200 nanometer or 150 nanometer, depending on how much thick you want your gold electrode to be. You'll deposit. So first we'll do chrome deposition, then we will do uh, gold deposition on the top. So and this we are doing for better adhesion. Not only chrome, like titanium is also used as an adhesive layer for gold as well. So platinum also requires some sort of adhesion layer like gold. So if you want to deposit platinum, generally we'll do titanium and platinum. So or chrome and platinum. Like if we just deposit platinum as such, it will not stick to your substrate and the metal will come off. Okay. So next we'll move on to problem 15. What is PDOT PSS? So you would have seen this mentioned in one of the lectures, right? Option A is a conductive and piezoresistive polymer. Option B is a non-conductive and piezoresistive polymer. Option C is a metal. Option D is a piezoelectric polymer. So what is the correct answer? So PDOT is a conductive polymer and it is also having a piezoresistive effect. Right? Okay. So the correct answer is option A. And like the full form for PDOT PSS is polyethylene dioxythiophene polystyrene sulfonate. Okay. So like unlike other polymers, this is conductive. So most of the polymers are like non-conductive, they're insulator like SU8. This PEDOT PSS, since it is conductive, it also has, in addition to its conductivity, it has piezoresistive property. So this is generally used in um, fabricating like devices where we like flexible devices or organic uh, semiconductor devices. So in those cases, we use this kind of polymer in order to make any piezoresistive structures. So in so these processes will be generally low temperature processes. We will not go to high temperature process. Okay. Next, we'll move on to problem 16. So in problem 16, we have silicon nitride is grown over cantilever for compensating stress in cantilever due to silicon dioxide. So this is it correct? Is it true or is it false? Okay, so let me draw a cantilever. So if I'm having a thin layer of silicon and let's say I'm having SiO2 on top here and doing deposition SiO2 silicon, and this is my cantilever anchored here. Excuse me. So like is it true or false that we are using silicon nitride to grow over a cantilever for compensating stress? And okay, so let me explain this question. So first, what do you mean by stress in the cantilever? Like what is causing the stress? Okay, so here you can see that what we are having is we are having some substrate which is having like some which is like say in the case of cantilever you can say it is like 10 micron or less than that thick, and we are having a film on the substrate. Okay, so let's say this film is SiO2 in our case. Sorry, so this is SiO2 in our case. Okay. Mm. And this is our substrate which is silicon. So like what happens is the deposition process happens at different temperature. So if it is PCVD, it will happen maybe at 200 degree or to 300 350 degrees centigrade. And then once the deposition is done, we'll come to room temperature. And these are two different materials, right? SiO2 and silicon are two different materials. They'll have different quotient of thermal expansion. So they will expand and contract at a different rate. So if we look at the quotient of thermal expansion for silicon, it is somewhat higher compared to that of SiO2. So what it means is that silicon will expand and contract faster than that of SiO2. So due to like unequal quotient of thermal expansion, what will happen is like when the film is very thin also, so it will have to follow the substrate in terms of like how it is expanding or how it is contracting. So if your SiO2 is like 500 nanometer and you are having 10 micron silicon, then like the silicon is having higher thickness compared to your SiO2. So like it is like this region is completely clamped, and like whatever rate at which this substrate will expand and contract, your film will have to follow it. Because of this, so SiO2 will have some thermal stress, and this is compressive in nature. Compressive means that like the film is compressed. So what happens is when we release, so the this is like it will be having compressive stress when it is in clamped condition. Okay, when we try to release the structure, like if we are trying to make a cantilever, and if we release the structure, what will the film will try is that it will try to reduce its compressive stress. It wants to go to some zero stress state. So, in order to reduce the compressive stress, if you are like having some elastic material, and if you are trying to compress it, once you release it, what will happen is that the material will try to expand. So that is what is happening here as well. The SiO2 will try to expand, so but the silicon is not trying to expand at the same rate. So what will happen is we'll have the cantilevers which are bending like this. Okay. So this is how a structure will behave if you are having some residual compressive stress. If there is some residual tensile stress, means in the case of silicon nitride, we have like residue tensile stress when we are doing deposition, and this is because the quotient of thermal expansion for silicon nitride is much higher than compared to that of silicon. So what happens is that there will be some residue tensile stress, means like the film is being stretched. Okay, the film doesn't want to get stretched, but it is being stretched because the substrate is having different quotient of thermal expansion. So if you are trying to stretch, like say a rubber band, you can take a rubber band for example. If you are trying to stretch it, and once you leave it, it will try to shrink to its original state. So that is what is happening here. So if there is a film which is having tensile stress, it will try to contract once it is released. So if you are having a cantilever with silicon nitride on top, it will bend like this. If you are having a cantilever structure which is having silicon nitride on top, then it will bend like this. If you are having a cantilever structure which is having silicon dioxide on top, then it will bend like this. And also this like with how much it the degree to which it bends will depend on like the thickness ratio between the SiO2 and the substrate, and also on the residual stress on each of them. Okay. This is for silicon nitride. This is for silicon dioxide. But when we fabricate cantilever structures, we don't want like this kind of bent structure because our performance will vary. So what we will do is, since silicon dioxide is having compressive stress, we can like deposit a material which will have tensile stress. So the overall stress of this will get compensated. And so in order to have this compensation of the stress, we'll have to adjust the thickness of the silicon nitride and silicon dioxide layers accordingly. So by having suitable thickness of silicon dioxide and silicon nitride, we can ensure that our fabricated cantilever is not bent in any particular direction. Okay. So that's why we are growing silicon nitride over cantilever for compensating the stress in the cantilever due to silicon dioxide. Okay. So now let's move on to next question. Problem 17. Why is primer coated before photoresist? So in I think one of the earlier problems, we would have seen that there is a step where we do coating, and before coating the photoresist, we are coating something called as primer. So option A is primer coating removes moisture. Option B, primer coating will clean the wafer. Option C, primer coating improves adhesion of photoresist with substrate. Option D, primer coating will improve alignment of the mask. So what is the correct answer? Okay. So before we look at the answer, let me say what are the steps. Let us recall what are the steps that are done. So first we will clean the wafer, then we will dehydrate it. So in dehydration, we are removing all the moisture. Then we will coat the primer. Then we will coat the photoresist. And then we'll do the exposure and development. So then we'll do soft baking. This is then followed by exposure, development. This is again then followed by hard baking and other subsequent processes. Okay. So we are not using primer to remove moisture. This is wrong. And we are not using primer coating to clean the wafer. We are using solvent cleaning or any other acid-based cleaning to clean the wafer. And it does not have any role in improving the alignment of the mask. So the correct answer is primer coating improves adhesion of photoresist with substrate. Okay, so there is one type of primer called HMDS, which is hexamethyl disilicane. That will so what this primer does is that it will modify the surface chemistry of the surface. So let's say if there are some hydroxyl bonds on like wafer, uh, like because we cleaned the wafer with water before, there will be some OH bonds on the surface. These OH bonds will not have a good adhesion with the photoresist. So if the photoresist is not having good adhesion with the substrate, what will happen is when you are trying to do development or something, the photoresist will just come off. So the regions where you wanted photoresist to be there, the photoresist will not be there. So in order to provide better adhesion, we will use primer coating. So another important role that this primer coating plays is that if you have a primer coating, we can reduce the thickness of the photoresist as well. So let's say you want, and why do we want to reduce the thickness of the photoresist? The thickness of the photoresist will affect the resolution of the pattern that we are writing. So resolution is the smallest feature that we can write, and it's generally measured as critical dimension. Like it is also referred to as critical dimension. If we have a thinner photoresist, then we'll have like smaller resolution. Like if you look at e-beam photoresist, okay, in addition to having different way of exposure, the resists are also very thin. And also even in optical lithography, there are wide range of like photoresist with different photoresist thickness. With photoresists which are having like lower thickness, you can have like smaller size features. And if you want to photoresist with smaller thickness, then you want if you're having somewhat rough surface or a surface which is not smooth or flat, which is not flat, then like if you are coating photoresist, you want to ensure that it will like there is some sort of uniform coating uh, over the rough surface and your photoresist is sticking on all the places, right? So we will use a primer coating for that case. So the correct answer is option C. Primer coating will improve adhesion of photoresist with substrate. And another important thing is it's always used in photoresist like which are having lesser thickness so that it will have very good adhesion to the substrate. And so its main important uses for improving the adhesion. So now let's move on to next problem, problem 18. Mask plate having transparent features and dark background is option A, dark field mask, option B, bright field mask, C, gray field mask, D, black and white mask. So I think this we saw in one of the previous questions. So what we have is we are having a mask plate which is having transparent features. So let's say we are having a square feature. So this is transparent and the remaining region is dark, means which is opaque. So what do you call this kind of mask? What do you call this kind of mask? The correct answer is dark field mask. So in dark field mask, we have large regions of large amount of opaque region, followed by small amount of transparent region. Mm. So next we'll move on to next problem. What is considered as the gold standard for breast cancer diagnosis? So gold standard means like it's a fail-proof method to diagnose a breast cancer. Option A is ETM phenotyping. B is MRI. MRI is magnetic resonance imaging. C is mammography and D is X-ray. So what do you think is the correct answer? Which one is considered as a gold standard for breast cancer diagnosis? Okay. So ETM phenotyping is what? ETM phenotyping is the electrical thermal mechanical phenotyping for which we are using a MEMS device. So it's not the gold standard that is used in hospitals, right? Currently, MRI and mammography, X-ray. So here, mammography is generally used for diagnosing and screening and testing. So this is for to detect the cancer, breast cancer, when it is most easily treated, and it uses X-rays in order to image the breast. Okay. So one important thing in this is that sometimes it can miss some of the tumors that are present, and it is a traditional technique compared to that of MRI. So in MRI, we use radio waves and magnets along with that in order to get like detailed cross-section images of the breast, and this can be studied at different angles, so we can easily find out like cancers that can not be detected by using mammography as well. So the fail-proof method is MRI, and you know that breast is a tissue, it's not a bone, so we cannot use X-ray as well. ETM phenotyping is we can use to find, but again it depends on the comparison between the properties of the tissue. So like unless we have a very like standard, some standard, and you know like the values will differ depending on person to person. It's not like uh, it will not have very fixed standard, regular standard. In the case of MRI as well as mammography, we are using images in order to find. In MRI, since we have very detailed images, we can find even tumors that are missed using mammography. So the gold standard for breast cancer diagnosis is MRI. So the correct answer is option B. Okay. So now let us move on to problem number 20. For that, any questions? So now let's move on to next problem. What strategy was used for making SU8 conductive such that it functions as an electrode? Option A, SU8 is a conducting polymer. B, mixed with PEDOT PSS. C, gold coating. D, by using high voltage across it. So what is the correct answer? What strategy was used for making SU8 conductive so that it functions as an electrode? So we already know that SU8 is a non-conducting polymer which is insulator. Okay. And in previous, I think one of the previous questions, we saw that we had deposited gold, like chrome gold to be precise, in order to make it function as an electrode. So the correct answer is option C, which is gold coating. So now let us move on to the next problem. Problem 21. The finer resolution in photolithography can be obtained by A. Blue light, B. UV light, C. IR light, D. X-ray. So IR is infrared. UV is ultraviolet. So here, and the resolution in photolithography will depend on the wavelength of the light. So smaller the wavelength, uh, better the resolution will be. Okay. If you look at the spectrum of various electromagnetic waves, we have radio waves which has the highest wavelength, and the smallest wavelength is the gamma ray. So as the wavelength is high, the energy will be low. So that is because the frequency is also low, and the energy of the wave can be given by h into nu, where nu is the frequency, or it can be given by h into c by lambda. C is the velocity of the wave and lambda is the wavelength. So if we have a large wavelength, the energy will be low and also the frequency is less. But when we have a shorter wavelength, we'll have higher energy and higher frequency. So in photolithography, we are mainly interested in this three types of wavelengths, and in this spectrum as well, depending on like a particular wavelength, we have different bands. So if we look at blue light, which is coming between 400 nanometer to 600 nanometer. So blue light is between 400 nanometer to 600 nanometer. UV light is between 100 nanometer to 400 nanometer. IR is between 800 nanometer to 1 mm. Okay. And X-ray, we do not use X-rays, even though it is having very small wavelength. We are not using X-rays in photolithography. Photo means what is light, but still we don't use any X-rays. So which is having the shortest wavelength? It is this UV light. So the correct answer is UV light. 100, which is having the wavelength between 100 nanometer to 400 nanometer. And why does the resolution like depend on the wavelength? Like why do we get finer resolution with smaller wavelength? The reason is that as the wavelength becomes smaller, the amount of diffraction that the wave undergoes also decreases. So if there is less amount of diffraction, let's say we are having some exposure, the light will not get diffracted much. So the features that we get from exposure will also we can easily obtain smaller dimensions by using this particular method. So the correct answer is UV light for this question. Next, we'll move on to next problem. Problem 22. The smallest feature that can be printed with adequate control using photolithography is controlled by. So here we want to print the smallest feature, and we are able to control this particular parameter. So option A, we have smallest image that can be projected on the wafer. B, resolving capability of photoresist. C, temperature of wafer. D, ion energy of ion implantation beam. So what do you think is the correct answer? So here in this question, what we have to find out is that what parameters we can change in order to have a very small feature. Okay. What do you think is the correct answer? Okay. So first, let us look at one of the each of the options. So the temperature of wafer does not play a role in the photolithography. Okay, so this is wrong. and we are not using any ion implantation beam during the lithography process. So this is also wrong. So now we have two other options. One is the smallest image that can be projected on the wafer, and B is the resolving capability of PR. So like we can control the smallest image that can be projected on the wafer. One way is by having even in photolithography there are different wavelengths that can be used, like 365 nanometer, 435 nanometer, um, and maybe 208 nanometer or so. So as we decrease the wavelength, we can control the size of the image that can be projected on the wafer. Also, in one of the previous lectures, we saw that there is something called as projection lithography, where we can use some objective lens in order to make the dimensions of the features that are projected on the wafer to be smaller than the ones that are on the mask. So that is one thing that we can control. Okay, so we can make sure that we have a very small size feature by making sure that the image that is projected on the wafer is small. So this is correct. And the second thing is the resolving capability of PR. So in one of the previous questions, I mentioned that the photoresist thickness also plays an important role. So if we have thicker photoresist, then you will need more amount of exposure dose or exposure time for the light in order to penetrate through the photoresist. And what happens is, like, if you increase your energy of the exposure or the time of the exposure, there is a chance that it will spread. So the features will become large, the features will become larger than what you want. Okay. But if you have a thinner photoresist, then the amount of energy that you want to use in order to expose the particular region can also be decreased. Also, the exposure time can be reduced. So the beam also, when the exposure beam, when it is falling on the resist, will not spread as much as we use a thick, when compared to that of using a thicker photoresist. What happens if we use a thicker photoresist but do not, if we reduce the energy of the uh, beam that is used for exposure, then what will happen is, as the beam moves to the photoresist, it will not be able to reach the bottom of the photoresist. So only this much regions will get, their solubility will change. So when you put it in a developer, what will happen is, if it is a positive photoresist, you will get something like this. So there'll be photoresist, some amount of photoresist that is present. And if you go for etching, then you will not be able to etch any of your sample. When you strip your photoresist after the etching process, you will be left with the silicon wafer as such. Okay. So for problem 22, the answer is option A, smallest image that can be projected on wafer, and B, resolving capability of PR. So this can be controlled by using different PR. So there are various PRs which are having a wide range of thicknesses, and we can also optimize the spin parameters of the photoresist in order to reduce the thickness. Then we can also play with the uh, size of the image that is projected on the wafer by using any suitable objective lens. So we can have features which are smaller than that in the mask. So we can improve our resolution. So the this is the end of this problem solving session. So any questions? So if you have any doubts, you can reach me at rainrjesma@gmail.com. So we'll be ending this live session. Thank you.